particular talk, we are going to cover more fundamental aspects of traditional programming in the multi-threading environment. So from an end-to-end understanding, I'm assuming that this is going to give a full, good understanding of how to build the systems from end to end. So we are going to cover the lock management framework that we use in one of our core analytical engine. DSHA, as some of you know, is a global investment management firm. And as a firm, we trade in multitude of complex financial instruments. And our systems provide the agility to scale to the dynamic needs of financial instruments and associated complexities. To put it simply, what it means is our systems need to model the finance entities in the financial domain and the associated relationship that exists within those entities. And our systems need to be performant, which means, in some of our systems we use multi-threading, and that multi-threading, as some of you may already know, comes with its own challenges. So how we went about addressing one of the challenges that comes in the multi-threading is going to be our talk today. To set some context, in order to increase the application performance, we often use multi-threading, right? And one of the most common problem that we encounter with multi-threading is the data consistency issues due to the race conditions. And to address the race conditions, we typically employ locking techniques. And as we try to increase the concurrency by resorting to more fine-grained locks, the complexity associated with the locks also increases, right? And this sometimes lead to deadlocks, right? And where one thread holding a lock on one object trying to acquire a lock on another object, and the second thread is already holding that object and waiting to acquire the first object, right? So both the threads wait on each other and they can't proceed further operations, right? How do we address this kind of problems, right? Typically, we carefully analyze all the locks in the system and try to come up with an order in which any thread should acquire the locks. Now, once we have this order defined and ensure that the threads are following this order, then we can avoid the cyclic dependency so that we don't run into the deadlocks. But, however, as a system state consists of objects related in certain ways, it is not possible to always ensure that all the transactions follow this order, right? Which means we might run into the deadlock. So the system should be able to identify these deadlocks as well as recover from these deadlocks. Building any concurrency software which is, which has good quality and reusability is hard. While in the languages like C++, Java, there has been a significant improvement, significant support added in the concurrency libraries, but this particular problem is so far, we haven't come across any solution. We looked at some of the built-in solutions also, as well as ready-made solutions. Since we couldn't come across any solutions, we went ahead and built our own lock management framework. Now we are going to talk about how to build such a framework so that anyone who running into these problems could benefit from it. Before we dig deeper into the details, let's try to first understand why a transaction and how a transaction need to access any object, right? A transaction might need to read the state of an object for its operation. So it needs to access the object in a read mode, which means like any other transaction which also need to read the operation, it can share that access with the other transactions also. Or some transaction might want to change the state of the object, so it needs to have an exclusive access, so no other transaction can have the access at the same time. So this defines the modes in which any transaction want to lock the object, which is shared and exclusive. Next comes like a transaction might follow the defined order, in which case we can consider that it is following the in-order strategy, or it may need to go out of order for the business use cases, where we say that this is following the try and retry strategy. The only difference between try and retry strategy is that whenever we run into the deadlock and the transaction need to be victimized, then the transaction gets aborted and all the locks that it is holding is relinquished. In the retry case, once it relinquishes, it reattempts to acquire the same locks again, so that until it is successful, it will, whenever if it runs into the deadlock, it releases and reacquires the locks. So once we have the locking modes and the strategy in which a transaction might want to acquire the locks, the next comes the validations that we may want to perform when a transaction is trying to acquire the lock. One of the validation is like, as we discussed, like, we need to ensure that the transaction is following the locking the objects in the predefined order. That is what we call it as a transaction based locking. Next comes, like since we talked about the locking modes, shared mode, exclusive mode, whenever a transaction is trying to acquire the lock, we need to make sure that the other transactions which are holding the lock are compatible to this particular request, and if so, then the transaction can get the lock. Now, once we have the validations in place and if all the transactions are following the right order, then we don't run into the deadlocks. But as we discussed, there would be cases where we run into the deadlock. So the system should be able to identify the deadlock, identify the deadlocks. For that, we use the typical OS concepts, like where we would have studied about the deadlocks between the processes and resources. Similarly, here also we need to build a wait for graph between the transactions. And whenever we have a cycle in the wait for graph, we can say that the transaction is running into the deadlock. And we need to find the transaction that needs to be victimized. So putting all this together, we need to understand the data structures that form the core of this, as well as the relationship that exists between the data structures. Now let's get into the how those data structures that we have. Like every transaction which is running in a thread will have an object called transaction descriptor. The transaction descriptor has an ID. This is a typical ID to identify any transaction, and it has the logs. It has the held list, which lists the logs that it is holding. Similarly, it will also have the list of logs that it is waiting for, and whether it is following the in order or try or retry strategy. Depending on that, the allow victimize flag will be set. After this, if a transaction is going to wait on other transaction because the other transaction is holding the log, it will have the wait for member populated with that other transaction. Next comes the lock object thing, where like any domain objects that you have in your application that you want to protect the access, those domain objects can extend. Those domain objects can extend from lock object. So this is the base class which forms the core, where we will be doing the validations and all. So the lock object defines lock priority. So any domain object can extend this lock object and can return the priority in which the object should be locked. And similar to the lock priority, this base class will also provide methods like lock manager lock, lock manager try, retry, and takes the lock mode. This is the methods which provides the logic to lock the object. Now once the object is locked, we have a lock entry which contains information like what is the lock object that it is encapsulating and the mode in which the lock object is locked, and what are the transactions holding the lock and the transactions which are waiting to acquire this lock. So this information is going to be captured in the lock entry. Now while we have the lock object and the lock entry which has this information, the other important piece is all the locking, all the access to the object should go through a common class, that is the lock handle. Now lock handle is the one which is going to use these methods and make sure that the transactions don't run into these problems. Bringing it all together, what happens when a transaction is trying to acquire the lock? So first, when a transaction instantiates the lock handle, and the lock handle internally is going to do the lookup in the domain object collection, get the lock object, and once it gets the lock object, it knows the mode and the strategy that the transaction is following to lock the object, so it will call the appropriate method on the lock object. And the lock object is going to validate as well as check whether there are other holders, waiters and all, and if all things goes fine, it returns the true to the lock handle, and lock handle now then get passed on to the transaction. Now once the transaction has the lock handle, then it can call any methods on the domain object using the lock handle methods. And it can call any methods whether read or write depending on the mode in which it has acquired the locks. Now let's get into the algorithm part, where what happens during the lock acquisition. Here you can see that whenever a transaction requests a lock object, first we check whether the transaction is already holding the object, because there could be a re-entrant lock, right? Once you lock an object, you may call a method that again requires the object to be locked. If it is already holding the lock, you can simply increment the reference count and return the object. But in case it is the first time the transaction is requesting the lock, check whether it is following the in the right order, or whether it is okay to be victimized, which means like, it is using the try and retry strategies. And if it is saying it is following the in order, but in case if it is actually locking in and out of order, throw the locking order validation, violation error. Otherwise, check whether the lock mode is compatible with the other transactions holding the lock. And in case if it is compatible, then return the lock handle to the object and transaction gets the lock. Otherwise, the build that wait for graph that we were talking about, because now we know that what are the transactions which are holding this lock, and so you can put the wait for of this transaction to the one that is holding and build a wait for graph. And if there is a deadlock, we need to next identify the victim and victimize that one. Otherwise, you need to add these transactions into the waiting list. Right now, let's zoom into what happens in the deadlock check. Like this is an example where two transactions, T1 and T2, are trying to acquire the two objects, O1 and O2. Right? For the sake of this example, let's understand that the order in which these objects need to be locked is O1 followed by O2. Now first T1 transaction is requesting the O1 lock, and since O1 is holding O1, it will be granted the access, and the holders of the O1 is populated with T1. And next when T2 comes and requests the O2 lock, T2 also will be given access and T2 will be added into the holders of O2. After that, assume T2 is requesting an exclusive lock, which is out of order, but since it is saying it is using that retry strategy, we don't victimize it immediately unless there is a deadlock. So what happens here? Like if T2 is requesting the O1 exclusive lock, then T2 will be added into the waiters of O1, right? Next, assume T1 also comes in and T1 requests the exclusive lock on the O2. Now T1 will be added into the waiters list of O2. Here if you see the way the wait for graph is getting built from that wait for member in the transaction descriptor, initially when T2 is added into the waiters, T2 is now waiting on T1. Now, and T1 also comes and T1 requests the exclusive lock, so T1 now is waiting on T2. So now this is the where the cycle is formed. So here we can assume that there is a system is running into the deadlock and identify the transaction which needs to be victimized. Since T2 is following the out of order, we can victimize the T2 and let the T1 continue with its operation. Similar to acquiring the lock, let's see what happens during the releasing a lock. Now, whenever a transaction releases a lock, now we need to check whether are there any other holders of the lock. If there are other holders, then it is possible that now that we are releasing the lock, the mode in which the object is locked can be degraded. Let's consider that a transaction is holding an exclusive lock and then it requested a shared, first initially it had a shared lock and then requested an exclusive lock. So we upgrade the lock mode to the shared to exclusive. Now when it releases the exclusive lock, then we can degrade the mode to shared so that if there are other transactions which need the shared lock can be continue with their execution. So check if we can degrade the lock and then after that see whether who are all the waiters of the lock. If there are waiters, then see whether the mode in which the waiters are waiting is now compatible with the new mode. If it is compatible, then you can go ahead and let the transaction continue with its execution by giving the access to the object, or else again we need to see whether there is going to be a deadlock by releasing this lock. So we'll see why this might run into the deadlock scenario here. And if at all there is a deadlock, then we need to again identify the transaction that needs to be victimized and victimize it. Let's see with an example here. So why the system can run into a deadlock while releasing a lock itself. So there are three transactions, T1, T2, T3. Each one of them is requesting the shared lock on O1 object. First say T2 is requested the O1 object in the shared mode, followed by T3 and followed by T1. So here the holders list of O1 will contain T2, T3, T1. Now let's assume that T1 now requested an exclusive lock on O1, right? So T1 will be added into the waiters list, and since the holder is T2, there is a wait for graph will get updated as T1 is now waiting on T2, right? As such there is no deadlock, so it will just be added into the waiters list. Then T3 comes, T3 requested the exclusive lock, and so T3 also will be added into the waiters, and since T3 is also waiting on T2, to release the shared lock, the wait for graph will get updated like T3 is waiting on T2. So here also again there is no deadlock as such, but if you think about it, there is a deadlock that is existing already. Right? Now when T2 comes in and releases the lock, we need to, then T2 won't be there here. So that means we need to update the wait for graph and remove the T2 transaction from the graph. And T1 will end up waiting on T3 and T3 will end up waiting on T1. This is where we now have a deadlock and we need to victimize either T1 or T3. So this is what happens while releasing the lock and how do we identify the deadlocks. Now we'll see a quick demo of with some sample applications.
Thank you, Ranadheer. In the next section, we are going to see the lock manager framework that we have built. How does it address the challenges that we saw in this framework through a practical demonstration? Before we move on to the scenarios, a few quick insights. For the purpose of this demonstration, we are going to leverage some of the basic financial concepts, just that of a stock and a portfolio. I'm assuming stock is something what will be known for everyone here. Portfolio is merely something which comprises of one or more stocks. And as we all know, as the stock price would change, it would impact the value of the portfolio. The next thing to know is that the predefined order here is that of a stock followed by that of a portfolio. What that means is the stock has assumed a higher priority here. In this demo, we're going to have 4 cases. The first one is going to focus on a happy path, followed by a locking order violations. Next, we'll show a deadlock scenario and how we handle a victimization. Let's go into our first case. As we discussed earlier, this case is that of a happy path, which means we expect everything to go smoothly and no error to be reported. As you can see, here we have a service which is the update price. What it is doing is it's first acquiring an exclusive lock on the stock, and then the transaction is acquiring exclusive lock on the stock followed by exclusive lock on the portfolio. This is a case as simple as it can be. Let's see how the system works in this scenario. We again have the predefined order here as the stock followed by portfolio. We'll start the server and then take a look at the logs. We're just keeping the rolling logs. However, we don't expect to see any error in this scenario. Next, we'll move on to a client terminal here. And the client terminal will get a handle to the server. This code is built using C++. Then we'll show the price of the stock as it exists now and show the details of the portfolio. Next, we'll try to update the stock price through the update price method that we saw earlier. As we can see now in the next line that the price of the stock has been updated and so has the value of the portfolio. Everything works smoothly, so nothing to worry in this case. We'll move on after this to our next scenario. Our next scenario would be that of a portfolio acquiring the lock first and followed by the stock. So what we have done is just reversed the lines or 1 and 2. Everything else in this case remains just the same. Stepping into it, this is a locking order violation scenario. So as the predefined order is different compared to what we are going in here, the system will default and show an error, which we expect to see in the logs. Just like the prior example, we'll again start the server here and take a look at the logs. In this scenario, we should observe the error in the logs later when the transaction has run. Let's move on to the client terminal and see how this scenario works. We'll get a handle on the server and after that we'll just update the price in this case. A quick thing, the first line there shows a order violation, and it also says the acquiring that lock, we are trying to acquire a lock of higher priority while already holding the lock of a lower priority, which is not something that the framework typically allows, and hence there's a locking order violation in this scenario. In the next example, we'll try to simulate a deadlock. Now, as we learned earlier, for the purpose of deadlock, we'll need two transactions. So the first transaction remains the same as our first example. However, we have introduced a second transaction. The second transaction shows portfolio details. In this case, we are applying, in the second transaction, we are first getting a lock on the portfolio, followed by the lock on the stock, which to iterate over and print all of the constituents of the portfolio. Since this is a read-only operation, we are only acquiring shared-only locks in the second transaction. Since this is a deadlock scenario, we are introducing a sleep of 15 seconds here. The reason for doing that is first we want, in the first transaction, to acquire a lock on the stock. As the sleep is introduced, the second transaction will come into play. At that point, the second transaction will acquire the lock on the portfolio, the shared lock, followed by the shared lock on the stock. In the meantime, the sleep would be over, and the first transaction would again go in and try and acquire an exclusive lock on the portfolio. As we can see, this would clearly result into a deadlock scenario. Here, we'll again start the server and take a look at the logs. Please note that in this case, both transactions are going in for in-order traversal. Hence, none of the transactions are expected to be victimized. We'll also need two terminals here. This is the first client terminal in which we are getting the handle to the server. Then, after that, we are gonna update the price on the stock. Moving on to the second client terminal, we'll again get the handle to the server and show the portfolio details. Now we'll move on to the logs and see that there would be a deadlock scenario. As you can see, that there's an assertion failure because there was no victimization allowed in this case. Okay. We'll then move on to our last scenario here. In this scenario, all that is changed is in the second transaction, we have replaced the strategy with the retry strategy, if you can see. What the retry strategy means is that the second transaction is declaring upfront that it is going for out-of-order traversal, and hence it is ready to be victimized should a deadlock occur. This is what makes the system intelligent enough to figure out which transaction to be victimized in case of a deadlock. In this case, we don't expect the server to crash as we would have expected in a deadlock scenario. Let's move on and start the server again and take a look at the logs. We'll again need two client terminals here, and just like the previous scenario, we'll be getting a handle to the server in the first one and updating the price of the stock. Then we'll move on to the second client terminal, again get a handle to the server and iterating over through the portfolio details. In this case, we expect a victimization. So we'll go to the logs and see how the system has handled that. Just scrolling through the logs, it shows that we are trying to acquire the log. The two different transactions are trying to acquire the log, and it will result into a victimization scenario. Yeah, if you can see, the system has detected that victimization and displayed that. Okay. These were all for the scenarios that we were to discuss today. Just as a quick summary, what we covered in this session was that a lock manager framework which addresses the concern where it goes in by default in order strategy. It handles different strategies, that of a in order, try and retry, and it also handles different modes of acquiring locks, which is shared and exclusive. The system is also intelligent enough to determine at the time of acquiring and releasing the lock if it can land up into a deadlock scenario. And if the transaction has upfront declared that it could be a deadlock scenario, then the system victimizes the transaction so that there are lesser server crashes. Our takeaway from this is while concurrency is the necessary evil, it's not that difficult to handle it. And a simple example like this or a framework like this beautifully captures that. So thank you for your time today at the session. We're open for questions.